From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
I'm tempted to and want to do is to really flip the way additive manufacturing is thought about right from the very first time you learn it. So at the moment we go through the process of we have a CAD model, and then you break that down through the steps, STL file, so forth, to printing parameters, set up your printer and print it. And I just think it would be beautiful to swap it so people first think, here's a nozzle, extruding material, and this is what happens if you move it at different speeds and different positions, and you get this blob, and then you get a line, and then you can get some strings and do all these different sort of geometries that are possible.
That was Andy Gleadall. Andy's a senior lecturer in additive manufacturing at Loughborough University. Since joining Loughborough University in 2017, his research has focused on material extrusion additive manufacturing in several areas, all enabled by microscale control of the print path. He developed and wrote open source software called Full Control G-Code Designer to control precise design for additive manufacturing. You can find it at www.fullcontrolgcode.com. Full Control was originally created for in-house research activities, but is now freely available to progress research into material extrusion additive manufacturing. It's been used for a wide range of applications, including process calibration, material characterization, tissue engineering, 3D printing electronics, pharmaceuticals, microfluidics, prosthetics, artistic creation, and to control auxiliary equipment for in-process monitoring. He strived to use rigorous engineering research to drive additive manufacturing and medical manufacturing beyond the current state of the art. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcasts, including Spotify, Apple, Amazon, or Stitcher. Andy, thank you so much for joining me today. I'm excited to talk to someone from one of my alma maters, Loughborough University, up in the Midlands. So
nice.
Welcome.
Thanks for having me. Nice to see you too.
Awesome. And let's just kind of get started from the beginning. I mean, you're kind of at the university teaching now, but like, what was the journey? Like, how did you get to that point and focusing on some of the additive manufacturing stuff that you're working on now?
Yeah, okay. So I started my PhD and that was on polylactic acid, but nothing to do with 3D printing. So for medical applications and simulating its degradation and properties as over time, basically mechanical properties. And then after my PhD, I then started 3D printing with this material, focusing on tissue engineering scaffolds predominantly. So for those scaffolds, they were using all the properties of biodegradable stuff that we've seen before, but also polylactic acid being a very nice material for printing was handy. But they were always needed intricate geometries where they were often very simple, but really precise in terms of a single extrusion and then a space and then another extrusion from a bioprinter where it's extruding the polymer as a cylinder with literally surrounded entirely by air. And then that's where in that air, that's the pores, that's where the cells would grow. So the actual space between filaments was your physical design. So there was not really a CAD model as much as the toolpath was the thing we were designing. So right from my first use of printers, I was pretty much writing my own scripts to generate the G-code to control the printer and tell it where to move in X, Y, Z, and also for multiple materials, so doing quite intricate things. So printing the polymer for a few layers and then printing the gel a little bit lower so that it doesn't overflow on top of the polymer and stop the next layers bonding to it and things. So that was when I was doing a research position after my PhD, and then about 4 years ago I became a lecturer at Loughborough, so I could just research anything I wanted to basically. And I kind of went back to my basics of mechanical engineering, which was my undergraduate degree and my PhD, and took the same material, same process that I'd been using, but then started to characterize its mechanical properties, but still thinking from the scale of these individual filaments. So we developed test specimens for testing the mechanical strength of a bond between just two filaments stacked on top of one another, and then walls of filaments stacked. But always just a single interface rather than a complicated tool path with lots of different settings and different orientations and things. And that gave really good mechanical properties. And I've kind of just gone from there into more and more complicated structures, but designing the actual tool path. And my students were doing that as well. And at a certain point, I realized my students were struggling with putting a lot of time into programming to generate the machine control code, the G code, when actually they just wanted to do the print, and they knew what they wanted. They wanted to tell the printer how to do that in a convenient way. So then I wrote software that was kind of an interpreter for their human description of the toolpath. So they say, I want a line from here to here, and I want a circle from here to here, and then I want to repeat all that for 5 layers. And for each layer, I want to increase the width a little bit to slightly change the pore size. So the software then that I wrote allowed them to write the features just how I've kind of described them there, and then it would interpret them, figure out all of the XYZ commands, how much polymer to extrude, and put that in the G code format for the printer to actually use. And that's kind of where I've been now hammering down for the last year or so, of saying that it's custom G code and explicit print paths are the way forwards for everything is what I'm claiming.
So taking a step back, I mean, I know next to nothing about kind of tissue engineering and some of the mechanics in there. I mean, high level, kind of what does tissue engineering mean, and kind of why are you using kind of this? Why is this technology a good fit, or the potential of this technology a good fit for applications within the field?
Yeah, so for tissue engineering, we're generally trying to grow a tissue outside the body often, but it can also be in the body. But growing a tissue to replace some tissue that has maybe been lost, say for replacing bone that's been taken away during operations. So we would typically have a scaffold that forms the overall shape of the structure, and then you can put cells in that scaffold that will grow and multiply and basically eat the scaffold away until there's nothing left except the bone cells in their original shape. And we can do this with various tissues like cartilage, bone, muscle, and sometimes you don't need the scaffold, sometimes you do. And the really good thing about this, most of my stuff is about extrusion additive manufacturing, which is basically getting material to extrude from a nozzle and depositing it where you want. And that's really an easy process compared to a lot of additive manufacturing processes in terms of material versatility, and it's quite gentle on the materials. There's no lasers that would be curing the material, which can damage cells. So it's quite nice for tissue engineering because we can extrude these gels which contain cells, like living cells, but they're being treated quite gently. So then you get a nice set of living cells without any damage from the manufacturing process.
And kind of talking more about kind of the journey with full control, like what kind of, as you identified this problem of like, hey, like I've gone down this path of writing my own scripts, but like my students or colleagues or anything who want to do the same thing, like it's just a big barrier and we're not getting as far. Was the idea like the industry is just not, or the academic research is just not getting as far because of this big kind of barrier to doing that?
So it was really just from my research initially. I never thought I would release full controls, and I don't know if I actually introduced and said what it is, but it's Full Control G Code Designer, which is basically the software I was previously talking about, where you are designing the whole manufacturing procedure, the G code, in this kind of parametric feature-based manner, kind of like a feature tree in CAD, but instead of creating 3D geometries, you're creating a sequence of instructions for a printer, which are often they're based on geometry, but not always. So yeah, initially I just thought this would be a really good way for my students to be able to do better research, do more efficient research, and that's when it started. Then I began personally to find it beneficial over writing scripts myself, which I hadn't really expected. And then I added more and more capabilities as I then set projects that could do more complicated things, and kept on pushing and really iteratively adding capabilities to this software. So initially it was just a line, and then repeats of this line, and then the ability to change, the amount of extrusion or how fast the line was moving. And then it kept on increasing with each sort of project and each new requirement. So it was always sort of driven by a specific project's requirements. I'd had the capability to do mathematical curves and things like change the whole geometry after you've generated the G code, and various other things that just kind of added to the capabilities. So then I always focused on capability rather than user friendliness, because it was always going to be a case of the more time I put into user friendliness, the less time I could put into capabilities. And then there was a sort of constant iteration on both sides, but definitely a focus on the sort of pragmatic interface, and it's built within Excel. So Visual Basic is the actual program, using Excel as an interface, which I really love. And I've written molecular dynamic simulations in Excel and things, because it's such a powerful user interface for putting data in and things. But now we're looking at then taking it to a more accessible format where it can be integrated with other software and have a more user-friendly operating, such, be web-based and things like that.
And what was it like? I mean, you're kind of in the academic sphere and kind of innovating this kind of software. Was it like a spin out? Was it part? I mean, obviously it's part of your research. Like, what was the dynamics there? Kind of building a pseudo company almost.
Yeah, it was. I've released it fully open source to sort of steer away from that side of thing, because my strengths are really in the technical research and the expertise of this process that we've characterized, the mechanical properties and all this stuff. With, I also enjoy design and creativity, but they're not my specific research, and certainly not software development. So I at one point was thinking, should I commercialize this? But I'd spoken to lots of people about it and found it was very hard to convey the benefits until I just show them the capability, show them a specimen that couldn't be printed or would be extremely difficult with the normal workflow of CAD, STL slicer and things. And I kind of realized I didn't want to go down the route of just putting all my effort into fighting to convince people it's worth them paying money on, and really just go down the route of doing really good research to get to the point where our capabilities were irresistible for people to spend money on. So that's the kind of direction I went. And I decided to release it open source much in the same reason, because I could see the benefits of it and the value, but I didn't want to focus all my efforts and time on making it so it could work on any operating system with guaranteed no flaws if you update Windows or something, because that needs a whole expertise in software engineering that I don't have. So I made it very powerful and pragmatic, as I say, with the idea being then I can improve it for specific industries or specific users as required, and let other people also put their expertise. And the open source community is really very amazing at lots of things. So releasing it in that way meant, I was hoping, and it seems to have been really successful, with really attracting people that just wanted to make it much better going forwards, and then it can have these commercial aspects potentially in the future, which is still not decided at all on that side of things.
And what is one of those use cases where having this tool really makes a difference? Could you kind of articulate that?
Yes, so there's a company I'm just talking to now. We're releasing a printer. I won't say the details and stuff because we haven't discussed about sharing that data, but they're releasing a printer, and we're going to use full control for them to give their clients two extremes of capability. One is really precise characterization of the process. So with full control, you can design really explicit controlled single lines of extrusion with parametric control over their spacing and their positions in the Z direction and everything, their speeds, all the details. So we can have a kind of parametric test print, which is kind of like what we do for our research when we're characterizing the process and characterizing mechanical properties. But it's a really controlled one where there are no other factors accidentally brought in that might depend on the user's slicer version and things like this. So this can then be used for the company that are developing these printers to put their expertise into calibration files, which you often see are supplied with printers, but these would be adaptable and far more comprehensive than you usually see, to make sure their customers really optimize their printer right from the beginning. And then they'll also use it as a showcase, because when you print with full control, you can control the printer in ways to achieve structures that are just impossible for a normal slicer. And that's in terms of the sort of geometries that you're printing, but also in terms of the quality, because you can design whole complicated print paths with zero travel and zero retraction, for example. It's just a continuous extrusion the whole way, which you'd never believe from looking at the design, for example. So this means they can show their customers the peak of what their system can do if they control it extremely well, and they have this expertise of design and of the process that the company and kind of I am providing, and also the really simple characterization stuff to make sure they're printing as well as they can. So this is two extreme kind of cases of where it's valuable, which is in an industrial setting. In terms of academia, it's kind of similar in many ways. I would design really complicated, intricate specimens that people couldn't do with slicing, putting in parametric capabilities, and then I can hand that over. And that's me putting my knowledge and expertise of the process into this adaptable design that then bioprinter users, who are not expert 3D printers necessarily, if they've come from a background of biomedical characterization things, they can benefit from all those capabilities that I've kind of put in there, and those strengths of the design, to get really good printing without having to spend days or months learning and optimizing the process.
Sure. And you've talked about this kind of term parametric a few times, so maybe we can kind of dig into that. So I mean, the way I kind of think about it right now, or like a simple way, is that there are certain things that are like most mechanical things that you see around, like they're extrusions of metal and they're rectangular or they have circles in them. But like if you look at nature, there's a raspberry that has all these like different shapes. That it's extremely hard to, like, how do you, like, pulling that in and printing it is actually not that trivial, or anything in your body that has different curves and shapes and porosity. And so kind of how do you think, I mean, you're solving kind of this big problem here about kind of doing parametric operations, but can you dig into that, kind of explain for maybe someone on the novice side that may not be familiar with the technology?
Yeah.
With that.
So, and parametric designing in CAD was a huge step forwards from before parametric design was available, where you can basically define some parameters, which might be some numbers for a box, say the width, the length, and the height, and then you create your box according to these three parameters, which you can then just change as you like, and the box will change its shape. So then you can put nice relative relationships between things. So if you change the size of an overall part, maybe the whole is parametrically defined relative to one face of that box, and then this whole that you've designed will move with the face if you extend it. And this is it's a hugely beneficial aspect of CAD. In the current workflow, you take that parametric CAD model and you'd be able to adjust it in CAD, create an STL file, and then send that to a slicer and do produce the layers and then the toolpath for each layer, and then build that together. And other additive manufacturing systems will have slightly different approaches, but in general, you do the CAD parametric design and then bring it through the workflow until you get your manufacturing control. What full control allows, you're designing all of the toolpaths directly, so that parametric control is put directly into the toolpath in terms of its information. So then if you adjust one parameter, you generate the toolpath straight away. So you don't have to go through this whole workflow, which means you can parametrically edit this file after it's been designed with these parametric things without having to do any of these extra steps, which is obviously very efficient. But it's also for the calibration side of things. It means we could create a test specimen, which might be several lines printed with different spacings and different widths or something, and then create repeats of this with parametrically varied properties. So then we can potentially in a few minutes print hundreds of different combinations of printing speed and temperature and layer height and extrusion width, or whatever parameters you might be using for laser-based processes or something. And it would be, every line can be individually controlled, which just wouldn't, there's no way to do that through the normal workflow. The way you would normally do that is to write a script which would generate this parametric toolpath, which is the kind of equivalent to full control if you're happy to do all the programming yourself.
Yeah, and it's such a big issue too, the more people move additive manufacturing into production ecosystems, like knowing about the nuances of the process. I mean, other than, hey, like I can drag a file, I can press print, but there's a lot of stuff going on in the background that can, from print to print or from part to part, even on the same build, can make a big difference in terms of your parameters, your ultimate quality, and even safety. I mean, if you're talking medical or certainly aerospace, automotive, like that understanding is critical.
Yeah, and the thing that CAD is sort of trying to push forward at the moment is putting more process data into the CAD model. So you might be able to say for different parts of your model, it's common that you say different tolerances and things, dimensional tolerances, but this might say then I'm going to use a different set of parameters for printing this section of the model than this section, and you can put that data in, and then going forwards you have different materials in different sections of your model, or different graded densities and structures which go towards the kind of mathematical model design, in which there are software around for that, which eliminate some of these issues. But the big problem for me is, as I see it, until you've designed the toolpath, you haven't got all that data about where the defects are going to happen and how those defects are going to happen. And also you can't optimize your design unless you're optimizing the toolpath if the defects are coming in from the toolpath generation. So in terms of the way you design things, there are common design rules which are supposed to make sure that what you're printing is kind of sensible and is well suited to the slicing software. And we're taking that to the kind of the next step, where you're truly designing for the actual assembly of these individual building blocks, a single extrusion. And that then lends to a completely new scales of design. So one thing we were recently publishing is how to, as you're printing a single line of polymer, you can vary its width on the fly. And that's just a really natural thing to do if you're designing an individual extrusion and you think, I want it to be different geometries at different positions along its length. Coming back to the tissue engineering scaffold, this means I could vary my pore size at different positions whilst still making sure my overall grid structure had the same overall shape, or sort of overall unit cells. So then taking this ability to then vary these extrusion widths and create different geometries is completely new. You can't do that with the normal workflow where you'd set a specific extrusion width for different parts of your model, because each continuous line of extrusion is seen as a single printing condition. Whereas what we're saying is that's what our basic building block is, kind of material coming out of the nozzle. And now if I move my nozzle around in different ways, I can get that material to deposit in different shapes and different sizes. And there's no longer this kind of idea of a single extrusion having a single width and height, and then you stack several extrusions next to each other to fill a gap. It can completely break away from that kind of way of thinking, that is dependent entirely on the toolpath. There's nothing in the CAD model that would link to that. You are truly designing the actual movement of the nozzle and its speed. So the only way really to put that into CAD would be if you were designing every single extrusion, which would just be impractical, and that's kind of just unnecessary. That's what I'm doing, but you wouldn't need a CAD model for it, because you've already got the toolpath. It's just a curve for the nozzle to follow.
And I suppose too, like this software really allows your students to get a deep understanding of all the process parameters that go into any of these extrusion technologies and able to change them and see it. I feel like that's a really powerful teaching tool. Like a lot of I mean, most universities now have some sort of 3D printing experience in the academic coursework, especially mechanical. Maybe it's just doing some prototyping or things like that. But as I see from graduates that come out, I mean, they know how to maybe operate at a basic level a printer, or say like, hey, we should get this 3D printed to prototype. But like that really deep understanding of, hey, like this is a pretty nuanced technology, like decisions we make early on make a difference. Like having that software like right in their face, like just highlights.
This is something I really am tempted to and want to do, is to really flip the way additive manufacturing is thought about right from the very first time you learn it. So at the moment we go through the process of, we have a CAD model, and then you break that down through the steps of STL file, so forth, to printing parameters, set up your printer and print it. And I just think it would be beautiful to swap it so people first think, here's a nozzle, extruding material, and this is what happens if you move it at different speeds and different positions, and you get this blob, and then you get a line, and then you can get some strings and do all these different sort of geometries that are possible. And then think, right, okay, so these lines of extruded material are quite a good building block to go up, and then build up to a ducting type product where it's thin walls or single filament wide. So that makes logical sense from single extrusion. You pack them together to get this duct, and then move up through to something more like an engineering topologically optimized bracket or something where it's now all really a complicated mixture of all different geometries everywhere. But still, it's got to be made out of single individual extrusions lined up next to one another. And I think it would be, I haven't done it because it's just so far away from what industry is doing at the moment that it wouldn't really be a fair thing on my students to say, this, that I think this is the best way, so you should all do it too. But the exception is for my project students, who because I'm talking about the additive manufacturing modules I teach on, this is for everybody. So they really need to understand additive manufacturing from the way most people use it. Whereas what I'm doing is very unusual. But for my group single, so individual project students, they know what they're getting into because they're choosing the project. I've told them this is going to be, doing something weird. But these students are doing things no one else in the world is doing at all. It's really, truly beyond anything some people are doing in industry or research anywhere for their specific thing. So last year there was someone printing stents with vertical extrusion of pillars of material, which just then the nozzle moves from the top of one to start printing the next. And it's just these 3D structures printed, which are impossible to do with slicing. There is no one doing this types of stents like this guy has shown, and he understood the process perfectly for that type of work. And that was following on from a previous student where she developed this from the ground up, starting with a box and then making it porous with very small extrusions, and then she turned that into these much more 3D stents with sort of, these are for heart valve or for blood vessel stents, with basically these kind of look like scaffolding around a building, if you imagine that, with vertical pillars that are exactly the same as the horizontal ones. And it's just a really natural process. As the person doing them for this project, he was able to really understand, when you tell the nozzle to extrude material, how long it takes for it to actually extrude material, and how fast that material comes out over time. So as he was extruding these vertical pillars of polymer, he was changing the speed of the nozzle continuously to make sure the strut was a constant diameter all the way up. So there was no such thing as a printing speed parameter. It was a constantly adjusted design variable for each individual building block. So really they're getting an understanding of the process that really would only exist for people that are developing the hardware, and still not for a lot of these aspects.
And it's been a while since I've been on campus, but Loughborough, in my mind, even it's gone on almost over a decade ago, has had a very strong additive manufacturing presence. So, I mean, which is still, I think, fairly unique in the world. Like, what sorts of opportunities are available within kind of the additive manufacturing kind of world at Loughborough? Can you just speak more broadly about kind of the community there, that's the research?
Yeah, so there's the strongest research is really going across multiple schools. So we've been building up ceramic research and electronics printing research, for example, which is then linking with the material school for making sure that the properties of those sintered parts, as they're being, say, sintered on the fly, as they're being manufactured layer by layer, are perfect. And then linking with the design school, who have a great reputation for additive manufacturing as well, for then putting these these solutions that are solved by additive manufacturing into neat packages, so they can be adapted to an individual patient, for example, because often a lot of medical aspects to this. And then I'd say in my specific group, I'm actually also in the mechanics and materials group, where we do quite a bit, but it's fundamental characterization of the process, and I'd say that is a real strength, where it's using the best kind of mechanics of materials research to understand this process at that scale, which is not the most necessarily what's the word not attractive, but very appealing way of doing it, because it's not doing something weird, wacky new material, which we've done as well. We've printed like moon dust and things like this, but it's really just logical, sensible research, which is where my passion truly is simplifying out all of the noise and the parameters that are not actually having a huge impact, but may appear to do so because they're indirectly affecting other things that are going on, and just doing really excellent mechanics of materials research and that sort of thing to understand the process and really push forwards to get for these true manufacturing. So we're not really focusing on prototyping at this stage. It's for manufacturing end use parts with as good a quality or as good a design 3D geometries as you can possibly get.
And for students, you mentioned you teach some courses specifically on additive, right? I think that's pretty unique in terms of just having a specific course dedicated to that.
Yeah, we definitely. We have a couple of modules that do it, and one of them is specifically on additive manufacturing, which is my module I lead. And actually, I think one of the great things for students is the access to printers. So this last year has been a little different with COVID, obviously, but before it was just there was a room of sort of 30 printers that the students could just come in and use as long as they've been trained once, and that was free to them to use. If they're using a huge amount of material, that would need to be discussed and make sure they've got their own stuff, but otherwise they could just come in and play around and see what they were doing, really look at the print, make sure it's working, fail entirely, make it really mess up, break the printers and all this kind of stuff, but then they get repaired and they get help on fixing them. So this real kind of independent use of the printers was a real benefit of that Loughborough's kind of undergraduate stuff. So all the stuff I'm talking about with my full control G-code designer is really putting research into teaching. But for most of the students, I think that access to the facilities to do their own hands-on teaching and being allowed to literally damage these machines, not through stupid stuff, but through actually trying to do something good. It's fine, because I damage machines when I'm trying to do them, and it's just part of the process. So that access and that kind of, and I felt it when I first joined Loughborough, kind of part of the team, where you're not calling any of the lecturers sir or anything. It's all just first name basis. The technicians just really helpful around there, and just sort of passionate about the process as well. That's really the strength. So I could definitely talk about my students doing excellent research and publications and stuff that have come out of that. But this is for a few students who done a very bespoke bit of additive manufacturing for the broader range. It's this team atmosphere that's really a selling point of Loughborough, without a doubt.
And what are you seeing in terms of, as your students graduate, or even kind of just generally, like you're tied in this industry, like what's the ecosystem around additive manufacturing like in the UK these days? I mean, there's certainly I see LinkedIn posts and things about a lot of cool activities going on, but like kind of what's your take on it?
Yeah, so again, this is one where a lot of my students will be going down the more traditional additive manufacturing route, which is fully expected because full control is so new. But there are actually a couple using it in industry at the moment, but it's actually been quite a range of students that I can think going into additive manufacturing industries. So there's one that's a research institution halfway between research and industry, where a couple of my students have gone, and one of them is specifically working on additive manufacturing and sort of developing new materials and things, or qualifying new materials or whatnot. Another one has gone to a similar kind of institution linked with more closely with Sheffield University, and again they're doing additive manufacturing with I guess probably from the skill set they got as students of the process in terms of really technically understanding it. They've both got jobs where they are technically, managing additive manufacturing processes directly. And there's another one working for three working for medical manufacturers directly, who have all been, my specific individual project students. So these are people that are taking the kind of research I'm doing, and then that seems to have a place in industry, although it's only just sort of taking off. But then the students who are not doing my specific kind of research area, I can see them also using additive manufacturing a huge amount in industry. So somebody was building a prototype for firearms, not for combat situations, but for show pieces and for horse stuff, whatever that's called. When you have very elaborate guns and things. But they were using the additive manufacturing to get these prototypes of them, and other industries are using it to do fixtures and jigs and more common stuff. But it just seems in a really wide range of things, mostly on that more conventional route of prototyping and fixturing, and the sort of the parts where they're not being put in the final thing. But then the other ones I'm talking about are really making end use parts to go inside human bodies and things like that.
And if people want to collaborate with you on full control, or if someone's in the US or elsewhere in Europe or even in the UK, like what's that process like? They can obviously go to the website, but like, are you looking for collaborators? Are there like opportunities where you see like, hey, I'd love to work in this space or anything?
Yes. So I'm being very open to collaboration as much as possible now. That's sort of part of my ambitions of releasing Full Control, was to take it forwards through collaborative work of benefiting Full Control, but also to do research with people that would just use Full Control as it is. And both of these things are happening. So for people that are just using the current version of Full Control, often I'll, collaborate just by talking them through the way, if they've got ideas for designs, but it's quite hard to learn and use Full Control. But if it's going to end up with really good research, which is good for my kind of career and my job role, then putting that effort in to help them develop those designs and do really good 3D printing that they couldn't do without it, particularly for interesting materials, is very exciting for me at the moment. So people are doing ceramics, glasses, metals, all this kind of stuff with extrusion is really something I'm keen to do, because I've focused my stuff on the medical polymers, which are very easy to print typically, and now taking my understanding from them to these more functional and high-end materials is really valuable. So that's one way. If people just get in touch with me, I'll either say, yeah, let's have a chat and get through it, or I'll point them towards other people that are using Full Control, or there's like a Reddit page where people can ask questions and and that kind of thing. And then the other side is developing full control for the next versions, which might do, very, very different things to what it's currently doing. So there, typically I've been talking mostly to people that can program and code much more than I can, because this is when you first open full control. This is the thing where it's really obvious the way to improve it. So that's going very well at the moment with them. But as we go forwards, it's going to be this range of people with different skill sets who would be valuable. Just the whole package of people that are going to be needed, from whether it's going to marketing at that stage, the website, writing supporting documents, troubleshooting, that kind of stuff is going to be very, very valuable. But for the time being, I think the most sort of useful collaborators are people that really believe in customized toolpaths are valuable for their situation. Because if I try to fudge full control to some application where you could just do it with slicing, it's not really of value to anyone just to show that. Whereas if we end up doing something where they really can't do it with slicing, then it's good, because they're going to get something they can't previously do, so they're going to want to continue and do more. And it's a great showpiece for other people to see what this person or this company has done, and then think, oh, we could do something similar, maybe a completely different application. But it's where people are struggling with slices, not offering them the control to edit all the things they'd want to do, which I think is kind of something you just if you're printing really complicated parts, then, and it depends, complicated is not the right word, but parts where there is too much going on for you to even know what you would change, that's not really going to be as suitable for full control. But where you want to do something really explicitly, and it's challenging to get it to do that. The slicing keeps moving the nozzle in all different positions, and you tried lots of different ways to try and get it to do a continuous neat toolpath, and it's just not doing what you want. That's the type of work where full control and explicit print path design would be really valuable. And the other one is just very technical calibration, characterization of the process and things like that.
Awesome. And we'll put all the links to your kind of webpage, Full Control's websites, when we post it. So
thank you.
Go check it out. So I want to thank you so much for joining the show today. This is a great conversation. I'd love to continue to keep in touch and see how this continues to grow, and the user community of Full Control kind of ranges out into the world, and see all the cool applications that can be leveraged with this.
Yeah, thank you very much for having me, and I hope in a year we might have another one, and it will be a completely different type of thing with incomparable capabilities, what it is now, and then maybe 3 years will be again something completely different. So I am definitely taking this forwards in various ways, particularly for multi-axis and multi-process hybrid manufacturing is where I'm personally driving it forwards now for because it's my personal research needs this, and I can see this being really valuable for typically more on the manufacturing final use parts rather than prototyping parts. So the need to have more control when you're doing more axis is clearly there. So I think that's a really valuable route, which I'll be pushing forwards with it.
Fantastic. Well, we'll keep an eye on it, and we'll love to continue to hear the story as it grows.
Great. Thank you very much.
All right. Thanks.